We're going to take a break from looking at some trig right now to talk about complex numbers, and then in a section after this we'll look at the relationship between trig and complex numbers. So some of this might be a review from algebra classes that you've had before. So first of all, a complex number in general form looks like a plus bi. A is the real number component, and then this bi is called the complex component. So we could have something like 3 plus 2i. Now I is a complex number. A complex number basically takes into account this I, this variable, or this constant that stands for the square root of -1. So that's kind of what we're looking at here to get started with, and it allows us to take the square roots of negative numbers basically. So I'm going to start here, and as we go through the lecture I'm going to add some things about how we add and subtract complex numbers and how we multiply and divide and simplify complex numbers as well. So to get started, let's go ahead and look at how we can rewrite some things like negative square roots of 100. What we want to do is we want to factor out the square root of a -1, and then I'll be left with the square root of 100. The square root of -1 we know is I. Square root of 100 is 10, so we would write this 10i. So we want everything in this standard form. So standard form is just what we have up above, the a plus bi. So in this particular case it would be 0 plus 10i, or just 10i. Now you usually write the I on the end like we see here, but you'll see in some other instances when we have a radical, sometimes we pull it out front just so we don't get confused as to whether it's underneath the radical sign or not. Let's look at some others. Let's look at the square root of -24. So again, we break this off into the square root of -1 times the square root of 24. Now we want to look at the square root of 24, and we want to factor it completely, meaning we want to pull out any factors that are perfect squares. So one thing that we can do is we can do this prime factor decomposition, and we can look at all the factors of 24 and then look for groups of 2 of them for perfect squares. So to start breaking this down, this would break down into 2 times 12. I drag the 2 along. 12 would break down into 2 times 6. Drag both the 2's along. 6 would break down into 2 times 3. So right here I see I have a pair, square root of -1, square root of 4, square root of 6. So this is 2 times 2 is 4 is here, 2 times 3 is 6. And the reason I want to pull out all the perfect squares is that's what the simplified form is. So the square root of -1 is I, square root of 4 is 2 root 6. Now we don't leave it as I 2 root 6, we usually write it as 2i root 6. Now there's no real component here, there's no 2 out front or something like that, it's just all complex. Now technically the way we should write this is 2 square root of 6i, but make sure if you write it like this that there's no way to confuse that this I is underneath that radical. So make sure you're always very clear on that. We can also look at solving equations, not just simplifying an expression, but solving an equation. So for instance, I could go ahead and look at solving something like 7x squared plus 2 equals -2x. And it says to solve over the set of complex numbers. Well, I'm kind of curious about this. Let's go ahead and see if we can graph this on the calculator to get any insight as to what's going on here. So before we can graph this, first of all, we need to get everything on the same side of the equation. So to graph this, what I would graph is 7x squared. I'd add the 2x plus 2 equals 0. So I have to have it set equal to 0. So let's go ahead and open that up again. So we go over here to y equal, we'll clear everything out. 7x squared plus 2x plus 2. We want to graph this. I may have to adjust my screen here, or my scale. I see something's going on right up here. So let's go ahead and change our window, let's say -20 to +20 on the x-axis, and the same for the y-axis. And again, I'm just randomly choosing these to see if I can get a better look at the graph. There's a zoom standard option you can use as well. So it looks like there's definitely something going on here. It doesn't look like it crosses the x-axis, so for everything that we've learned before, it looks like there's no solution. But the key here is there's no real solution. I want to get a little closer to see what's going on near the origin. So I'm going to adjust this -5 to 5. Let's see what we have here. So there's our graph. Now this could possibly be coming down somewhere else over here. Since it's a second degree polynomial, I already know kind of what this shape should look like. So that's what the graph looks like. I'm going to go ahead and copy and paste this into the lecture so we can have that to refer back to. A couple things to remember here. I do not see this crossing the x-axis, so to me there's no solution. And there's no real solution is how we should think about that. So it could be a solution, there could be a complex solution, but the only things that will show up on our calculator are real solutions, meaning numbers like 2/3 or 4/5 or 7 or 9. Let's go ahead and paste that graph in as well. So it looks like no real solution. So I'm going to go through and I'm going to see if I can find any complex solutions. So what this means is it never crosses the x-axis. There's no real solution. So in order for me to solve this or figure out what x could be equal to, I need to probably use a quadratic formula because I don't see that this factors nicely into a product of binomials. So let's go ahead and use the quadratic formula. So the quadratic formula is x equal negative b plus or minus the square root of b squared minus 4ac all over 2a. Now this negative out front always has to be there even if the numbers that I pull from the formula have a negative as well. So you need the minus from the formula, think about it almost opposite, and any values that come from what we're graphing or what we're looking at. Now before I can use a quadratic formula I need to have it in standard form, which this is. Standard form means it has to be set equal to 0. So I pick off my coefficients here. So a is 7, it's always what's in front of the squared term. B is 2, it's always what's in front of the x term. And c is the constant, meaning what doesn't have an x term here. So I know my values for a, b, and c, and what I'm going to do is to go ahead and plug in and solve. So x equals the opposite, so there's my minus sign from the formula, 2 plus or minus. I always need to put this in parentheses because sometimes that might be negative, and that will matter whether it's 2 squared is 4 or negative 2 quantity squared is 4. So again, it matters, we have to be careful about that. Minus 4 times a times c all over the whole fraction 2 times 7. I want to make sure the square root sign goes clear to the end. So here I get x equal negative 2 plus or minus. This would be 4 minus 2 squared is 4. Minus 7 times 4 is 28 times 2 is 56. So 4 minus 56 all over 14. Okay, so negative 2 plus or minus the square root of 4 minus 56 would be a negative 52 all over 14. Now 52 does have factors that are perfect squares. You can use that factorization tree, and again, we're always going to have to simplify these, so knowing your perfect squares would be a good idea. So negative 2 plus or minus root 4. Actually, let's pull out that square root of negative 1 first. Square root of negative 1, square root of 4, square root of 13 all over 14. And again, we want to simplify this further. So x is equal to a negative 2 plus or minus, square root of 4 is 2, square root of negative 1 is I, so plus or minus 2i, square root of 13 doesn't break down any further, over 14. Now this is not in a plus bi form. We need to put this in a plus bi form, so I need to split this up into two different fractions and simplify. There's two ways we can do this. Negative 2 over 14 plus or minus 2i root 13 over 14, and then of course 2 goes into 14 7 times, 2 goes into 14 7 times, and I'm left with negative 1/7 plus or minus I root 13 over 7, or square root of 13 over 7, and then again make sure that I is nowhere near that radical. So this is standard form, and this has two solutions. One solution is negative 1/7 minus root 13 over 7i, and the other solution is x equal negative 1/7 plus the square root of 13 over 7i. Okay, so those are my solutions. Now, if you wanted to, you could plug this in and check your answers. So it's not a short process to do this. Let's go ahead and recall what our original problem was. It was x squared, or what, 7x squared plus 2 equals negative 2x. So that was the original. And what I want to do is I want to plug one of these in just to see if I get a true statement or not. And then it's easy to update and fix the other one, or check the other one. So 7 something squared plus 2, and I want to check, does this equal negative 2 times something? So negative 1/7 minus the square root of 13 over 7i, and that's going to be squared, don't forget. And I'm going to plug that same value in over here and see what we get. Now let's go ahead and pull in our calculator. I need to make sure my calculator's in the correct mode. Now degrees don't matter here, degrees or radian don't matter here, but see where this says real? I want that to be complex, or a plus bi. So let's go to mode, and if we scroll down here, radian, here it is, right next to real. I'm going to make sure I'm working in the complex number system, so a plus bi. So now notice that changes here. So I'm going to plug in the left-hand side here. So 7, open parenthesis, I'm going to use my fraction key, and I'm going to have a negative 1/7 minus another fraction, square root of 13, 7, and then our I. Now our complex number I is right here above the decimal, so I have to go second decimal, and that gives me an I. Close parenthesis and square it, and go plus 2. Now this is the left-hand side. Okay, so I get this complex number. Now on the right-hand side, I'll have a negative 2, open parentheses. I'm going to go for that fraction key, negative 1/7 minus that fraction key again, square root of 13 over 7, and then I, our complex number, is right here. That's second decimal, or I. So I'm going to hit enter. And this doesn't quite look like it matches. I have the 1.03 that matches. So what I can do here to make sure the decimals are the same, let's go here to math decimal. And I can see that this matches identically. So that tells me that that is a solution, and you might want to check that, especially on a test, because then you would know if you had the right answer or not. And of course, we can't use this to do the work. We can, however, do it to check our work. Now if you wanted to check the other solution with the negative 1/7 plus, it's pretty easy to just go through and edit that and change these to plus signs here, and then compare them. So the solutions check. And again, it's a good thing to go through that process to check it. So that's a quadratic formula. You can use a quadratic formula on anything that's to the second power, and you can use it even if you're missing terms. So for instance, what if you didn't have something like an x term, you just had x squared and a constant? That's okay too, because then that middle term b would be 0. So you're going to definitely need to know the quadratic formula for the exam, so it's a good one to put on a note card. Now some quadratic equations that you're asked to solve, the quadratic formula works for all of them, but sometimes there's a little bit different approach that we could look at. So x squared equals negative 81. So if I looked at this one, let's say I'm going to graph it, and I would get x squared plus 81 equals 0. This does not factor. And because it does not factor, I would have to use something like the quadratic formula with this. But one thing I do notice, that both sides are perfect squares. So I could rewrite the left side, or just keep it as x squared, and then rewrite the right side as root negative 1 root 81. Go ahead and take the square root of the left, and I'd have x equal plus or minus, because I have a primary and a negative root, or a principal and a negative root. Square root of negative 1 is I. Square root of 81 is 9. So x is equal to plus or minus 9i. And there's your solution. Now if you wanted to use the quadratic formula on this, that's okay too. In this case, a is 1, b would be 0, and c is 81. Because again, I get my c here, my a here, there's no x term, so that's why b is 0. So using your quadratic formula is going to have to be something you get really good at with these complex numbers, and also simplifying these expressions. So you're going to be using a lot of algebra here, and again, you have to be able to show your work and show your steps, because there won't be any credit unless you have work to support your solutions. A couple other problems we can look at. I'm not going to solve all of these. Some of them I'll just get set up for you, and then I will show you what the final solution is, and if you get stuck finding it, I'm happy to help. So here we have 4 times the quantity x squared minus x equals negative 11. This does not look like it's in a standard form. So standard form here would be ax squared plus bx plus c equals 0. To get this into standard form, we would distribute, and I'd have 4x squared minus 4x, and then I'd add the 11 across, equals 0. Now again, I can try and factor this. You could graph it to see if it crosses the x-axis. That might give you a hint what's going on here. But you can always use a quadratic formula. So on this one, we'll want to use the quadratic formula. And when we use a quadratic formula, I'm going to get 2 solutions eventually. And again, go ahead and double check this, and if you get stuck on it, let me know. You would get x equal 1/2 plus or minus the square root of 10 over 2i. Now remember, make sure that I is never anywhere near that radical. You don't want to look at that and think, oh, there's an I under the radical. Okay, so you have to be very careful about that. Okay, so those are some examples of solving equations. We could also look at simplifying some other expressions or multiplying. These would be called monomials. So the square root of negative 3 times the square root of negative 3. Now we need to be careful here. I can combine these under the same radical, but what ends up happening here is I have to be careful because they're both negatives. So if we rewrite this as the square root of negative 1, square root of 3, square root of negative 1, square root of 3, and I can group these together. This would be square root of negative 1 is I, square root of negative 1 is I, root 3 times root 3 is root 9, square root of 9 is 3, and then I times I is I squared. So this is 3i squared. Now we've only looked at i's so far. We've never talked about I squareds or I cubes or anything else. So let's go ahead and look at that right now. So I is the square root of negative 1. I times I is I squared, which would be taking the square root of negative 1 and squaring it. The square root and the squared would cancel each other out, and it'd be left with the radicand underneath, or just negative 1. Now I cubed would be I squared times I to the first, if you want to look at it like that. I squared, we know from up above, is negative 1. Negative 1 times I is negative I. Let's look at I to the 4th. That would be I squared times I squared. I squared is negative 1 times negative 1 is positive 1. And when we get to I to the 5th, we're going to see that that's just I to the 4th times I. I to the 4th is 1. 1 times I is I. And this ends up repeating. These are the only 4 possible values you can get when you take I to a power. Is negative 1, or sorry, I to start with, and then negative 1, negative I, and 1, and then it starts all over again. And we'll be simplifying quite a few more of these, but in this problem right here, what I need to know then is that I squared is equal to a negative 1. 3 times negative 1 is negative 3. Now if you forget these, your calculator can help you with this. So again, you have your I key down here. So if you wanted to figure out what I squared is, you can take I to the 2nd power. You can see you get negative 1. And actually we could do this whole problem. Square root of negative 3. You have to make sure you're in complex mode though. If you're in real mode, it's not going to help you here. You got to be in complex mode. 2nd square root negative 3. You can see where we get negative 3 back. Now, quickly you can do these on your calculator, but again, an answer is not going to earn you any points. It's your work that you show to get to your answer that matters. So make sure that on a test that you're definitely showing all of your work, because again, that is how you will earn points. So that's multiplying. Those are monomials multiplied together. Let's go ahead and look at some other ones as well. I want to make sure that we look at some that kind of have some strange cases maybe. So let's go ahead and look at multiply. This would be the square root of negative 27 times the square root of a negative 5. Now, right now it looks like they have really nothing in common. But again, I can pull out that square root of a negative 1, square root of negative 1. 9 times 3 is 27. So I want to break that out in such a way that I have a perfect square. And then I'm left with the square root of 5. So again, I times I, square root of 9 is 3. And then I'm left with root 3 times root 5, which don't simplify further, so I'm just left with the square root of 15. So I times I is I squared times 3 root 15. I squared is a negative 1. So I'm left with negative 3 root 15. Now this particular problem, there's no i's left because everything was raised to an even power, and with those even powers, the i's are gone. So negative 1 or 1. But when I have an odd power like I cubed, I to the 5th, you'll be left with an I. We can also do something similar with division. So if we divide here, I could have the square root of a negative 405 over the square root of a negative 81. Again, I'm going to go ahead and pull out that square root of negative 1 top and bottom. Now 405 is divisible by 9 at least. I think we could break it down into root 9, root 9, root 5. And then down here, the square root of 81 is a nice one. So simplifying, these cancel. Square root of negative 1, top and bottom cancel. Square root of 9 is 3. Square root of 9 is 3. Square root of 5. Square root of 81 is 9. So I have these canceling. 3 times 3 is 9. And I'm just left with the square root of 5. Okay, so that's how it simplifies. Now, if you want to, if you're given a problem, let's say this, I can just rewrite this underneath one entire radical in the numerator and denominator. So I can separate a product by radicals, and I can also do the same with a division or putting the numerator and denominator under the same radical as well, and simplifying under the radical and then kind of going from there. So you can rewrite these as such. We can go ahead and work with these with multiple terms in the numerator and denominator as well. And I can also work with these division problems with binomials in the denominator. So let's go ahead and look at 5 plus 2i over 1 plus 3i. Now our directions here are to divide. When you divide complex numbers, you multiply top and bottom, numerator and denominator, by the conjugate of the denominator. And the reason we choose the conjugate is when I FOIL it out, first outside, insides last, it's the difference of perfect squares is what I come up with. So it works pretty slick. So 5 plus 2i over 1 plus 3i. And again, I want to multiply top and bottom by 1 minus 3i. We choose 1 minus 3i because it's the conjugate of 1 plus 3i. So what we're doing here is we're FOILing this out. FOIL is an acronym for first, outside, insides, and last. So you'd FOIL them out, or you can use the box method, whichever way you learned. I'm going to be using the box method here, and sometimes I'll use FOIL as well. I just want to make sure that you know how to use the box method. So in the numerator, I'll have 5 plus 2i. So I have that up here. 1 minus 3i, which is down the side, and then what I do is I just fill in 1 times 5 is 5, 1 times 2i is 2i, 5 times a negative 3 is a negative 15i, and then I have a negative 6i squared. So this will not only just work with binomials, this will work if you have 4 terms times 2 terms, or 3 terms times 2 terms. So this will work for anything, whereas FOILing will only work with a binomial times a binomial. Okay, so from here I can take these terms then, and I would have 5 plus 2i minus 15i minus 6i squared. Well, combining like terms, 2i minus 15i is a minus 13i, I squared is a negative 1, plus 6. 6 plus 5 is 11. 11 minus 13i. That's my numerator. Now let's check the denominator. Now the cool thing about what's going to happen in the denominator is because I multiplied by the conjugate, all my I terms should go away, and I should just be left with a single constant. So this is 1 plus 3i, 1 minus 3i. And again, we fill in the box. 1 times 1 is 1. 3i minus 3i minus 9i squared. So this diagonal cancels. So I'm left with 1 minus 9i squared. I squared is negative 1. 1 plus 9 is 10. And then I need to put this in complex form, so that's a plus bi form. So I split this up into two different fractions. Real component first, complex second. And there's my simplification. So again, I have to be able to show all of this work, but I can check it with a calculator as well. So let's go ahead and pop the calculator in. Couple things to remember when you're using your calculator. It has to be in complex mode. Up here you can see that's a plus bi. So let's go ahead and put this in as a fraction. Alpha y equal 5 plus 2i. The I is above the decimal, over 1 plus 3i. Okay, and enter. So I get 11 tenths minus 13 tenths I, which is exactly what we have here. So again, you should check these on your calculator. There's really no reason to get a wrong answer on an exam because I can always check my work, and if I have it wrong, go back and find my mistake. So again, take the time to check these. It's a good thing to do, especially on a test. Now let's say on the test you just wrote in this answer with no work. There would be no credit. And most problems are worth 10 points, or they're multiple parts that are in total worth 10. So you don't want to do that. You don't want to get 0 points, so make sure you show your work. So this is our check, but remember you must show your work. And your calculator needs to be in that complex mode. Okay, so when we're simplifying, it's important to keep in mind that you always need to simplify completely, and you need to simplify always to a point where you have any factors that are perfect squares pulled out. Now we've talked about multiplication in a simple sense, and we've also talked about some division, multiplying by the conjugate in the denominator. Let's also talk about addition. So if we had a problem like 3 plus 6i plus 4 minus 5i, I don't have to distribute anything here. Distributing a positive doesn't change anything. So I can just go ahead and drop the parentheses. So I have 3 plus 6i plus 4 minus 5i. And what I do is I combine the real components, so that would be the 3 plus 4, plus the complex components. So these are real, and these are complex. And remember, I want to put this in standard form. Standard form is a plus bi. So this would be 7 plus 6i minus 5i is I, so 7 plus I. Now you can check this on your calculator as well, but again, you have to be able to show your work. So in parentheses, I'd have my 3 plus 6i. I is above the decimal, plus 4 minus 5i. And you can see that we're at 7 plus I. Now, always be sure that you are in complex mode. So when I paste this one in, I want to make sure that I note that we are in complex mode right here, a plus bi. So this will work with addition, subtraction, multiplication, division. To always check your work, you have to be in complex mode though, so always double check that. Now when you're working a problem with subtraction, you have to be really careful that you distribute correctly. So let's look at a little bit longer problem. 2 minus 7i minus the quantity 3 plus 4i minus the quantity negative 1 minus 11i. Again, you can put this in your calculator to check it, but you have to show your work. So what I'm going to do is I'm going to take this negative and distribute it here, and this negative and distribute it through here. So this would be a minus 3 minus 4i plus 1 plus 11i. So I'm going to group all the real components. So it'd be 2 minus 3 plus 1. And then I'll group all of the complex components as well. So that would be minus 7i minus 4i plus 11i. So 2 minus 3 is negative 1. Negative 1 plus 1 is 0. Negative 7i minus 4i is a negative 11i. Plus 11i is plus 0i. This one wasn't a very exciting problem. So everything simplifies to just 0. And again, you can plug this into your calculator and check it. Now, most of the problems we've been looking at so far with multiplication have essentially been monomials. Here we did some binomial work. Let's go ahead and look at a problem where the specific goal is for multiplication with binomials. So don't forget, if you have something like 3 minus 9i quantity squared, this does not ever equal 3 squared minus 9i squared or something like that. Never. This means to take 3 minus 9i and multiply it by itself. Now if you want to FOIL this out, you can. Or you can use the box method like we've talked about before. So this is going to be 3 minus 9i, 3 minus 9i. So 9, negative 27i, negative 27i plus 81i squared. 9 minus 54i, the 54i comes from combining this diagonal, plus 81i squared. And again, I squared is equal to a negative 1. So it would be 9 minus 81 minus 54i. 9 minus 81 is a negative 72 minus 54i. And again, it has to be in that a plus bi form. Now let's say we're looking at a radical with the I. Sometimes you might see it written as I root 5, or you could also see it as root 5, but this I has to be very clearly not under that radical, so you have to be really careful about that. So multiplying binomials, I would always recommend checking your work, and after you check your work, on your calculator, if you have a mistake, you can go back through and check anything by hand. You might also run across a problem where you have a monomial, so in this case we'll say 7i times some sort of a binomial squared. So what I would want to do here is write out what the meaning of this is. Now remember, 3 minus I quantity squared is not 3 squared minus I squared. That's not what this is. Okay. So what we can do from here then is I can go ahead and take 3 minus I times 3 minus I and then distribute the 7i, or I can take the 7i and distribute it through to the 3 and the I, but not to both, just the first one. I think the best thing to probably do here is to off to the side do your 3 minus I times 3 minus I. Now box method would work great here, but we can also just use the FOIL method. So 3 times 3 is 9 for the first. Outsides would be a minus 3i, insides would be a minus 3i, last would be a negative times a negative is a positive I squared. Now remember, I squared is a negative 1. So 9 minus 1 minus 6i, so this is 8 minus 6i, and that's what goes here, 8 minus 6i. So 7 times 8 is 56i, minus 7 times 6 is 42i squared. Remember, I squared is a negative 1, so I have 56i plus 42. However, this has to be an a plus bi form, so I'd write this as 42 plus 56i. 42 plus 56i. So always keep in mind that standard form. You have to split it into a real component and a complex component. It has to be very, very clear. Now we've talked about simplifying powers of I, like I squared, I cubed, and we had that nice little chart. Let's create another one, and then let's create a way for us to predict what's going to happen with larger powers of I without having to write them out from scratch. Okay, so I was just the square root of negative 1, which is just I. Then we had I squared, I cubed, I to the 4th. I squared would be square root of negative 1 times the square root of negative 1, which is going to be a negative 1. I cubed would be I squared times I, which would be negative 1 times I is a negative I. I to the fourth would be a negative 1 times negative 1, which is 1. Now I to the fifth starts this whole process over again because I have an I to the fourth, which is 1 times I. 1 times I is I. I to the sixth, and again, what we can look at here is just I to the fourth, I squared. So that would be 1 times I squared. 1 times negative 1 is negative 1. I to the seventh is going to be a negative I. I to the eighth is I to the fourth times I to the fourth, which is 1 times 1, which is 1. So you're going to see this whole trend start over again now. I to the ninth, I to the 10th, I to the 11th, I to the 12th. And it's going to return again, the same exact pattern. I to the 13th, I to the 14th, 15th, and 16th. Now what we don't want to do here though is have to write this out, let's say 100 times if I'm trying to figure out I to the 100th. Okay, so how am I going to do that? Well, it looks like to me, if I could figure out and pull out however many I to the fourths that are possible, what I could do next then is I could see the remainder. And the remainder should only be I squared, or I cubed. So let's try and look at that pattern. And basically what ends up happening is if I could have this memorized, I have all of them memorized. And again, if you forget those, you can put them on your calculator and double check them as well. So let's look at some different powers here and see if this will work. So let's look at I to the 21st. Now if I wanted to, I could write out all these i's. Let's do something smaller actually. Let's do I to the, I guess 21st. I don't want to write out 21 of these, but I'm going to do it once. So we'll see a pattern here, and once we see that pattern, then I don't ever have to do this again. 4, 8, 12, 16, 17, 18, 19, 20, 21. Now here's an I to the fourth. 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 And then here's this I by itself. So I to the fourth, we have this memorized, and if you don't, you could check it on your calculator. I to the fourth is 1. So this would be 1 times 1 times 1 times 1 times 1, which of course is 1. 1 times I is I. So my answer here is I to the 21st is just equal to I. Well, what I could have done is I could have just figured out what my remainder is. So 4 goes into 21 5 times. 5 times 4 is 20. My remainder is 1. So this tells me that I can ignore all powers. I'm left with a remainder of 1. So this would be the same as I to the first, which is just I. So I'm going to divide by 4, look at my remainder, and work from there. So let's look at I to the 14th. Again, if you want to write out all the i's, you can, but you don't want to keep doing this because what if we had I to the 215th? Okay, so we don't want to get into that. So I'm going to take 4 into 14. 4 times 3 is 12, remainder of 2. So this would be the same value as I squared. I squared we have memorized as to be a negative 1. Okay, so this is the same as negative 1. We can also have negative exponents. We could have something like I to the negative 26th. So what I'd want to do, the first thing is to flip this. The negative in the exponent says to flip this. Now 6 times 4 is 24. So if I divide 26 by 4, I'm left with a remainder of 2. So this would be the same as I squared. I squared is negative 1, so this entire thing simplifies to negative 1. And again, you can check this on your calculator, just make sure you're in complex mode. If you're not in complex mode, then a lot of times you'll get an error. Let's look at another example. What about I to the negative 35th? Actually, let's put this one in the denominator. So let's look at 1 over I to the negative 35th. Well, with a negative exponent, what I do is I flip it from wherever it is to the other numerator or back up to the other denominator, kind of depending on where we're at. Okay, so this would flip up top, so I'm left with I to the 35th. So if I want to look at this, I want the highest power of 4. So that would be 4, 8, 12, 16, 20, 24, 28, 32. So this would be I to the 32nd, I cubed. Well, this is I to the 4th to the 8th times I cubed. And I'm doing the same thing I did up here with the long division, just showing you one more approach in case you didn't like that one. I to the 4th is 1, so this is 1 to the 8th I cubed. 1 to the 8th is just 1, and of course we know I cubed from up here is equal to a negative I. And if you forget that, you can plug it into your calculator as well. This is the work that needs to be shown if you want credit. You can't just plug in this to your calculator and get a negative I and get credit. You will not get any credit. So again, you have to be really careful about that. Make sure that you always show all of your work. Okay, so let's go ahead and look at one last question. This one, we already know how to do this, but it might throw you off just because it looks so different. So let's look at negative 3 over I. Now you might look at this and say, oh, I don't have a conjugate here. You know, a conjugate of 2 plus I would be 2 minus I. I don't have that. But what I can do here is just multiply top and bottom by I. So this is a negative 3I over I squared. I squared is negative 1. Negative divided by negative is a positive 3I. So that simplifies as such. And again, it's just we're still applying some of the same rules. I don't need to worry about the plus or minus here. If you wanted to multiply top and bottom by a negative I, you could. It's not going to end up mattering. You're still going to get the same answer in the end, but just using the I is a little bit easier here. So as usual, while you're working, if you have questions, please let me know. Just send a quick screenshot of the problem and your work, and I'd be happy to help out. Good luck.